Hey there, science fans! Welcome to an exciting journey into the amazing world of stretching and squashing. Have you ever stretched a rubber band or squashed a marshmallow? When you do that, you're changing their shape. It's a simple yet fascinating way to see how objects can transform. In the world of mathematics, we can perform similar transformations using special tools called matrices. These matrices are like magical tools that help us understand and manipulate shapes and spaces. Think of matrices as magic mirrors that can stretch, squash, rotate, and even combine these transformations in various ways. They help us visualize and solve complex problems in a simpler manner. Now imagine drawing an arrow on that rubber band. What do you think happens when you stretch it? As you stretch the rubber band, the arrow stretches too, right? This is a great way to see how objects can change in size but still keep their basic shape. But what if there were special arrows that only stretched or shrunk but didn't change direction? These arrows would be quite unique, wouldn't they? These special arrows are called eigenvectors. They have a unique property where they maintain their direction even when stretched or squashed. And how much these eigenvectors stretch or shrink is determined by their partners in crime, the eigenvalues. Eigenvalues tell us the factor by which the eigenvectors are scaled. Together, they help us understand the deeper mechanics of transformations in mathematics. Matrices are like grids of numbers. They're like secret codes that tell us how to transform something. Think of a video game character. We can use a matrix to move it up, down, left, right, or even make it bigger or smaller. Each number in the matrix plays a special role. It tells us how much to stretch or squash in a particular direction. It's like having a control panel for transformations. Now for the stars of the show, eigenvalues and eigenvectors. Let's dive in. Remember those special arrows on the rubber band? Those are the eigenvectors, our key players. They're like the directions that only get stretched or squashed by the matrix, but don't change their direction. And the eigenvalues? They tell us how much the eigenvectors stretch or shrink. They're like the zoom factor on a photocopy machine, adjusting the size. Finding eigenvalues and eigenvectors involves a bit of math. But don't worry, it's not as scary as it sounds. These special numbers and arrows can actually make understanding complex systems much easier. We use a special equation that looks like this: AV. This equation might seem intimidating at first, but once you break it down, it becomes much more manageable. Don't let the symbols scare you. They are just tools to help us understand how things work. Think of them as a secret code that, once cracked, reveals a lot of useful information. A is our matrix, V is our eigenvector, and lambda is our eigenvalue. The matrix A represents a system or transformation, the eigenvector V shows the direction, and the eigenvalue lambda tells us how much the vector is stretched or shrunk. This equation basically says that multiplying the matrix A by the eigenvector V is the same as just multiplying the eigenvector V by the eigenvalue lambda. In simpler terms, the matrix transformation doesn't change the direction of the eigenvector, only its length. It's like saying stretching the arrow with the matrix is the same as just stretching it with a zoom factor. Imagine you have a rubber band. If you pull it in one direction, it stretches. The matrix is like your hand pulling the rubber band, and the eigenvalue is how much it stretches. The eigenvector is the direction in which you pull. This concept is very powerful in many fields, from physics to computer science and even in economics. Section 5. Eigenvalues and eigenvectors in action. From video games to real life. Eigenvalues and eigenvectors are everywhere in our technological world. Video game designers use them to create realistic movements and animations. Imagine a character jumping or a ball bouncing. Those movements are all thanks to eigenvalues and eigenvectors. But it's not just video games. These mathematical superheroes are also used in facial recognition software, Google's PageRank algorithm, and even in predicting earthquakes. Section 6. Why Eigen? A peek into the origins of a cool name? The word Eigen comes from German, and it means characteristic or own. It's like saying these vectors and values are special and unique to the matrix. They reveal the matrix's true nature, its hidden talents. So when we talk about eigenvectors and eigenvalues, we're talking about the matrix's own special vectors and values. It's like discovering its secret identity. Section 7. Beyond the flatland, eigenvalues and eigenvectors in higher dimensions. So far, we've been talking about stretching and squashing in 2 dimensions like on a flat piece of paper. But guess what? Eigenvalues and eigenvectors can work in 3 dimensions, 4 dimensions, or even more. Imagine a balloon being inflated. It expands in all directions. Eigenvectors and eigenvalues can help us understand these multidimensional transformations too. Section 8. The whirling world of rotations, eigenvalues and eigenvectors in action. Rotations are another type of transformation, and guess what? Eigenvalues and eigenvectors play a key role here too. Imagine a spinning top. The axis of rotation, the imaginary line it spins around, is like an eigenvector. It doesn't change direction, it just stays put while everything else whirls around it. Eigenvalues and eigenvectors help us analyze and understand these rotations, which are essential in fields like physics, engineering, and computer graphics. Section 9. A real-life spin. Rotating by 30 degrees. Let's say we want to rotate an object by 30 degrees. We can use a special rotation matrix to do this. The eigenvector of this matrix would be the axis of rotation, the line that doesn't change during the rotation. And the eigenvalue would be related to the angle of rotation, in this case, 30 degrees. Eigenvalues and eigenvectors help us break down this rotation into its essential components, making it easier to analyze and manipulate. Section 10. The power of eigen. Why these concepts matter. Eigenvalues and eigenvectors might seem like abstract mathematical concepts, but they have real-world applications in fields ranging from computer graphics and data analysis to physics and engineering. These concepts are not just confined to the pages of a math textbook. They are actively shaping the world around us. They help us understand and manipulate transformations, making them essential tools for solving complex problems and advancing technology. For instance, in computer graphics, eigenvalues and eigenvectors are used to perform operations like rotations and scaling, which are fundamental in rendering realistic images and animations. So the next time you see a video game character move, remember that eigenvalues and eigenvectors are at play, ensuring smooth and accurate movements. These mathematical tools are crucial in creating the immersive experiences that gamers love. Similarly, in facial recognition software, eigenvalues and eigenvectors help in identifying and verifying faces by analyzing the unique features of each individual. This technology is becoming increasingly important in security and personal identification, or even think about the forces that shape our universe. In physics, these concepts help scientists understand complex phenomena, from the behavior of particles to the dynamics of galaxies. They provide a framework for making sense of the natural world. Remember the power of eigen. These mathematical tools are not just theoretical, they are practical and powerful, driving innovation and discovery in numerous fields. These special numbers and arrows are working behind the scenes, making our world a more understandable and technologically advanced place. From the smallest particles to the largest structures, eigenvalues and eigenvectors are integral to our understanding and advancement of technology and science.